Hello students, welcome to this short little video on Chapter 10, Non-Linear Programming. So it's very similar to the material we've covered so far in earlier chapters in terms of linear programming. The only difference here, it's non-linear, so there's some key differences that we'll go into. So as it says there, the problems generally fit linear programming format, but they contain non-linear functions, and therefore are termed non-linear programming NLP type problems. The difference is the curves we're going to draw are not going to be straight lines, and it's very difficult to, the more complex and more difficult to pinpoint the optimal solution and optimal regions. Difficult, but as it says there, it's not impossible. The example we're going to go in is on page 478 of your textbook. We're going to work through this example. It's a nonlinear profit analysis trying to determine the best price or the price that will maximize our profits. So I'm going to go into Jamboard here and draw some things out. So this question is from, as I said, from Chapter 10. Page 478. So a couple of things that we know is that we're trying to maximize our profit. So Z is going to be our profit. It's going to be basically total revenue minus total cost. But we're going to break down total revenue to be price times volume minus our total cost is going to be based on our fixed costs and our variable cost. Fixed cost in this example is set at $10,000, and our variable cost is $8 per unit. So of course, the more we produce, the higher our variable costs are going to be. The question is, at what price should we set, or what should we set our price at in order to maximize our profits? One other equation that we know is that volume is based on our demand, and our demand is 1,500 units minus 24.6 times price. So this ends up being a downward sloping curve. It's a demand curve. Let me put that in here. This is basically our demand. So this comes from the question. So this is something that would be determined to be our demand curve. I'm going to go into an Excel file here to showcase what we can do with this. Oops, that disappeared too. Okay, here we are. So ignore everything I have on the left. Basically what I want to do is enter some possible prices. So I'm going to start at $10. I'm going to kind of go up to about maybe about $45. And our volume, remember our volume is based on an equation, 1,500 minus 24.6 times our price. So I'm going to put that equation right in here. Our volume, our demand is 1,500 minus 24.6 times this price unit here in cell G6. So at price, at $10, we would then have a demand of $12.54. If I copy this down, you can see that it's downward sloping. The higher the price, the lower the amount that will be demanded, lower quantity demanded. That makes sense. What we can do is we can graph this. I'm going to insert a scatter diagram here, and we can see that. There it is, that downward sloping demand curve. What we want to do is we want to determine the price that will maximize our profits. So go back to our whiteboard here, or smartboard. We can write this equation here, basically looking at this equation right here. Oops, can't draw straight. Yeah, it looks terrible. Let's go someplace else here. So our profit is going to be price times our volume. our volume, so let's put that up here again. So volume times our price minus our fixed cost minus our variable cost. Volume is 1500 minus 24.6 P. That represents our volume times our price minus our fixed cost, which is given at $10,000, minus our variable cost, which is $8, times our volume, times 1500 minus 24.6 P. So if we can solve this out. This is our Z formula. We can solve this out, but really what we need to do is take that understanding of how we calculate profit, total revenue minus total cost, put that into our Excel equation here. And what we can do, let's move this graph, is we can calculate the profit that would occur at each of those price values and each of those at each of that volume. So our price equation here is going to be our total revenue is price times our volume minus our total cost, which is $10,000, minus our variable cost, $8, times the value in cell H6. And there's our profit. Oh, that's not too good. Minus $7,492 at that price. So basically, we're not making any money. We're losing a lot of money. Our variable cost is $8, and we're only selling it for $10, so we need to sell a lot more units or increase our price. So with this formula, as is right now, we can copy this down, and we can see that our profit increases. Generally, kind of maximizes right around that $35 limit. Then it starts decreasing. Because of the exponent in it, because there's a squared function in there, it's going to have this this type of nonlinear relationship. See, as our price increases, profit increases until it's maximized at that $35 point, and then it decreases. We want to figure out what that actual price is. We know it's right around $35, but we want to be more exact. So what we can do is we can set up a little data table like this. Let's put in a price in there at $10. You can see that I have, what we can do is create the same profit function. Profit function is based on these values here, so it's C5, price, times C4, our demand, minus C6, our fixed cost, minus our variable cost, times our demand. Our demand is given to us at, and that's something we'd need to enter into that cell, 1500 minus 24.6 times our price. So we can go in here and we can basically change our prices, and you'll notice that when price is 20, our profit matches that value. It's the same formula. When our price is 30, it matches this value, 67.64 as our profit, and of course 35. But we don't want to keep doing that. We want to go like maybe 36. It's a little lower now, so it's somewhere between 35 and 36. We don't want to do that. What we can do is in Solver, we can use this solver function, solver tool. So we want to maximize our profit. So we're maximizing where we have that profit, C3, by changing values in our price. We're only adding that one, changing the variable, changing the price. Now, of course, our profit and our demand is based on that price. So after we change price, our demand and profit will change. So we're trying to maximize, find the best profit at the best price. So it's nonlinear. We need to change the solvent method to GRG nonlinear, and we solve it. We get this price there, 34 0.4878. So basically, you know, to the nearest penny, $34.49. The good thing with this is that if our, say, variable costs were to decrease, we could just change this one value here. You'll notice that in the table and in the graph, our values will change as well. So our variable costs, say we're able to produce the product for cheaper, so $6 instead of $8. Our costs change, as you can see there. Our variable costs changed to $6. Our table changed. I had to change some of the cell locations in our table calculations, but we can see our chart. And we can basically determine that our best price is going to be somewhere around the 30, maybe a little higher than $35. We can solve this just like we did before, maximizing the profit while changing price. Nonlinear. Best price is $33.49. So if our fixed costs were to change, say now perhaps utilities and rent is higher, it's now $12,000. You can see our graph is changing, our table is changing, and then we need a new price. And there we go.